Hi, I'm Carson.
And I'm Justin, and we are going to talk about memristors today. So, to get you started, you have resistors, capacitors, and inductors. So you have voltage and current, which can, in between is the resistance. And you have voltage and charge, gives you capacitance. And then you have current and flux, which gives you inductance. So that covers three, but there's this fourth missing link, and there's a basic passive element called memristance, which makes up this link. And that leads us into what is a memristor. So this is a fourth class of electrical circuit that joins the resistor, capacitor, and inductor at the nanoscale. And it completes the fourth side of the square in this image. So a passive circuit element that maintains a history of applied voltage by a memristance function is what this does. So this allows multiple petabytes of memory, 1 petabyte to be exact, to be addressed in 1 square centimeter of space. So that's a lot of memory in a small amount of space without having to constantly apply a voltage to keep it up. How a memristor works is the level of resistance varies as a function of its flux and charge, and this gives you memristance, which is a charge-dependent resistance. So how this works is you can think of it as a water pipe, except in this case when water flows in one direction, the diameter of the pipe increases, or in this case resistance decreases for the memristor. So when water flows in the opposite direction, the diameter decreases, and in this case for the memristor, the resistance increases. This allows you to put different resistance levels on the memristor, and then it'll store that as non-volatile, so you don't have to apply a constant voltage or other form of charge to have it hold its memory.
To give you a brief overview of the history of memristors, in 1971, Leon Schwa of UC Berkeley thought that this missing link between charge and flux could be found. In 1972, he and his student Sung-Mo Kang published a paper entitled Memristance Devices and Systems in the Proceedings of the IEEE generalizing the theory of memristors and memristive systems. In 1998, Bhagwat Sarup, William Nest, and others published a paper entitled Programmable Current Mode Hebbian Learning Neural Network Using Programmable Metallization Cell in the Proceedings of the IEEE International Symposium on Circuits and Systems, and demonstrating that the complexity of an artificial synapse can be minimized by using an ionic programmable resistance device. In 2006, HP Labs intentionally reduces the memristor to practice, showing that it is possible. In 2008, Dmitry Strukov, Gregory Snyder, Duncan Stewart, and Stanley Williams of HP Labs published an article in Nature, The Missing Memristor Found, identifying a link between the two-terminal resistance switching behavior found in nanoscale ecosystems and Leon Schwa's memristor. Stanley Williams created the first practical model. In 2009, HP Labs proved that the memristor can be stacked, allowing 4 to 8 times more memory on a single chip. In 2009, NIST scientists demonstrate flexible memory, which has memristor properties. In 2010, the possibilities of what a memristor can do started to be explored, and HP Labs proved that the memristor can perform digital logic in addition to storing data. In 2010, HP Labs and Hynix Semiconductor Incorporated enter into a joint development agreement to bring the memristor to the market. There are many different types of the memristor, one being molecular and ionic thin film memristive systems. These are made out of titanium dioxide resistors, polymeric memrisistors, manganite memristive systems, resonant tunneling diode memrisistors. The second is spin-based and magnetic memristive systems. These are called spintronic memristors. Yiran Chen and Xiaobin Wang, researchers at the disk drive manufacturer Seagate Technology, described 3 examples of possible magnetic memristors in IEEE electron device letters. Spintronics is at the heart of recent advances in hard drive data density and the niche non-volatile memory known as MemRAM. When I had mentioned in the previous slide in 2009, NIST scientists demonstrated a flexible memory which has memristor properties. That was their effort to build the first non-volatile, fast, flexible memory for defense purposes, and it led them to the invention of the first ever flexible memristor in July. This memristor uses the same material of that of HP's memristor, but in a much simpler way. Other types of memrisistors to be developed could use the magnetoresistive memory effect, electrostatic effect, valency change effect, thermochemical effect, phase change memory, nanomechanical memory, and ferroelectric tunneling.
So, memristors' function are to store data. Now, the thing is memristors can go above your typical binary storage of 0 or 1. They can store bits of just 1, but they can also store multiple bits. There are 6-state memristors, and they're already looking into 10-state and possibly 16-state in the future, depending on capabilities. A lot of this is dependent on the noise and level of determination, how accurate you can read the different resistances. So as technology advances, this will increase, and you could have one memristor that could store a whole hexadecimal number. The applications of memristors are numerous. They can be used as non-volatile memory, and they're pretty fast. HP's latest memristors can store a bit of data in less than 100 picoseconds, and this time light itself would only have traveled an inch, so it's quite fast. There are also low power and remote sensing applications for memristors. They can also be used as crossbar latches, as transistor replacements or augmenters. They can do analog computation and circuit applications, and they can also be used in circuits which mimic neuromorphic and biological systems, and like those are applied into learning circuits, kind of just like our brains ourselves can learn. And then they can also be used in programmable logic and signal processing. As you can see in the diagram on the right, why memristors are such an innovative technology and why they're being heavily looked into is just kind of like we did on our last cache homework. We learned that a 50% increase in CPU speed only leads to about, 9% increase in overall speed up, but a 50% increase in your hard drive and other memory leads to a 69% speed up. This is where if you can have all of your memory be very, very fast, the speed up would be great enough that it would invalidate the need for hard drives and flash memory such as DRAM, which it is faster than. It is still about the same speed roughly as SRAM. So as you can see in this image, just by making it so all your memory is just almost as fast as your CPU, the speed, you would have no delay time or latency really compared to what it is now for looking into memory.
Now, why use a memristor? What is the motivation to develop this technology? Well, one, it's non-volatile, like we had stated previously, so you do not need constant charge. This would mean computers could shut down and start right back up from where they left off. They use less energy and produce less heat, and it would allow for the logic and computing to be done at the bit level. Memristors could represent an artificial brain. Physarum polycephalum could be used to make memristors. This is a slime mold that has some of the same properties of a memristor. Since a memristor can hold a range of values between 0 and 1, it can have multiple states instead of just a yes or a no. This will help when creating artificial intelligence. The companies that are researching memristors today are Unity Semiconductor, AMD, Micron Technology, Samsung, and HP. Currently, the memristor is still in the development stages. HP was building the machine off of memristor technology, but making memristors commercially is still not doable yet. Producing them is not efficient and it is not cost effective.
In conclusion, the memristor is going to revolutionize the 21st century as radically as the transistor did in the 20th century. It'll still take a few years to get them to be commercially viable. They can make them currently, but they just can't do it in a commercial setting and do it repeatedly in large volumes. And then after that is accomplished, the performance increases after that will be beneficial to all, from just general users to supercomputers and on. It really will make a difference in the world of computing. Thank you.